What if I told you that this is the Earth's true shape? No, it's not a sphere. It's not an ellipsoid. And it certainly isn't flat, obviously. The shape that most closely reflects its true form is the geoid. The Earth's shape is actually unique, and to describe it in detail, we would need to map every centimeter of its surface. However, this creates a lot of problems for us, both because of the practical difficulties that doing so would involve, and also because very often, rather than an exact shape, what we actually need is a good approximation, so a geometric model. That's what we need for GPS coordinates, just to give you an example. So, just as there are different types of map projections for different purposes and applications, each model for the shape of the Earth has its pros and cons and is useful in specific situations. As early as the 3rd century BCE, certain scholars began to argue that the Earth was not flat, but spherical in shape. For example, Eratosthenes reached this conclusion by measuring the inclination of the sun's rays at different latitudes, and he also managed to make an initial estimate of the size of our planet. Today we know that his calculations produced a result indicating that the Earth was 1 to 2% larger than it actually is. Considering that these measurements were made 2,300 years ago without the use of any special technical instruments, it's a truly impressive result. However, centuries passed and numerous physicists and astronomers continued to study the subject until one of them had an insight. The Earth was not perfectly spherical. The physicist who came up with this revolutionary idea was none other than Sir Isaac Newton, the father of the theory of universal gravitation. In the 17th century, Sir Isaac Newton realized that the Earth, rotating on its axis, could not be a perfect sphere. In fact, the centrifugal force due to its rotation is greatest at the equator and smallest at the poles. And so, logically, our planet should have a slightly flattened shape at the poles. It's a bit like pizza dough. If I spin it around, it flattens and spreads out. Today, we can say with certainty that Newton's hypothesis was correct. The Earth has a radius of 6,378 kilometers at the equator and 6,356 kilometers at the poles. Of course, we're talking about a difference of only 22 kilometers between measurements of thousands of kilometers, which is tiny, so the image of the ellipsoid is obviously deliberately exaggerated. However, this difference is indeed enough to say that the Earth is not spherical, but rather a rotational ellipsoid, and there's a really important consequence to this conclusion. Pay attention now, because this is kind of the crux of the matter, and it's that the force of gravity is not the same across the entire planet. If the Earth were spherical, every point would be at the same distance from its center. Therefore, excluding the effects of topography and any internal irregularities within the Earth, the force of gravity would be the same everywhere. The problem is that, even in Newton's time, they realized that the gravitational force varied with latitude and was not always exactly equal. This is indeed perfectly explained by the ellipsoid model, since if the Earth is flattened, it means that at the poles we are slightly closer to the center of the planet. And therefore gravity there will be slightly stronger compared to the equator, where we are slightly farther away. So, according to this model, if we weigh ourselves at the equator, we are lighter than we are at the North Pole. Great. So, if we look at it this way, it seems that we have solved the problem and that the Earth is indeed an ellipsoid. And in part, we can say that this is true. In fact, as I mentioned previously, the ellipsoid is a useful geometric model that, for example, the GPS system uses to track coordinates. In reality, however, it was soon realized that the ellipsoid, although accurate, is not the model that best represents our planet. There is an even better model, and that's the geoid. The geoid has a strange shape. It's not a geometric solid like a sphere or a rotational ellipsoid, for example. Therefore, for example, its surface area and volume cannot be calculated using geometric formulas. There's no mathematical formula that describes the shape, because it's a shape that's derived a posteriori from the Earth's actual form. In fact, if we look at it, it resembles a slightly deformed potato. You might think that the elevations you see correspond to large mountain ranges and similarly, that the blue patches represent the oceans. In reality, that's not exactly the case. The geoid represents how the force of gravity varies on our planet, both in intensity and direction. In fact, scientists realized that the ellipsoid model is fine for coordinates, but if we start making precise measurements of gravitational force, it doesn't vary only according to latitude. There's something else we need to take into account, and it's what's under our feet. For example, if there's denser material deep below the surface, the gravitational force in that area will be greater. Conversely, if it's an area with less dense material, the gravitational force in that zone will be slightly weaker. These differences deform the Earth's crust, causing it to deviate from the perfect ellipsoid shape. Let's look at a concrete example to understand this better. Here in the Indian Ocean, we have a large blue patch, which means that there is less dense material underneath, resulting in a weaker gravitational force compared to the surrounding areas. Therefore, the geoid is lower than the ellipsoid we saw earlier. By the way, just as a side note, this is the largest negative anomaly on our planet, and it's probably due to the presence of low-density magma beneath this portion of the Earth's crust. Conversely, here in the Atlantic Ocean, we have a red patch, indicating that there is denser material beneath it and therefore more gravitational force. In any case, I should point out that the elevations we see in the geoid appear gigantic only because the vertical scale has been increased. All things considered, the difference between the geoid and the ellipsoid comes down to a few hundred meters at most, which is really tiny. When compared to the size of the Earth and to the naked eye, it would be impossible to notice the difference between one model and the other. Obviously, this model, although more accurate than the ellipsoid model, presents its own problems. As we discussed earlier, it's difficult to make measurements on the shape because we don't have geometric formulas like we do for the ellipsoid or the sphere. The use of one model over another, therefore, depends on what we need to do. If we need to calculate the distance between two coordinates, we might use the ellipsoid. However, if we need to compare atmospheric properties, or if we want to search for a metal deposit, a dense material found beneath the Earth's surface, then it would be better to use the geoid. Alright guys, thanks for watching up to this point. I hope you enjoyed the video and that it helped you understand this whole geoid story a bit better. I realize it's not a simple topic, but it's good to clarify things, and above all, it's important to highlight the fact that the Earth is not flat. See you again soon for the next video, always here on Geopop Everyday Science.